NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
NASA engineers have re-established communication with the Voyager 1 spacecraft, Earth's most distant emissary.
These rings, however faint, increased the mystery surrounding the gas giant. In addition, earlier theories concerning these far-off celestial entities were called into question when Voyager 2 discovered that Europa, one of Jupiter's 53 named moons, had an icy crust more than 60 meters thick. This discovery opened new directions for planetary science research by enticing scientists to explore the possibility of ice moons being habitable. The Voyagers received a vital gravity boost following their mission at Jupiter, which gave them the necessary push towards Saturn. Without this essential push, they would never have been able to break free from the gravitational pull of the Sun and travel farther into space. Soon after, Voyagers 1 and 2 split up, each traveling to uncharted territory. Voyager 1's trajectory brought it very near Titan, the moon of Saturn, which is enveloped in a thick orange atmosphere. Scientists' curiosity over Titan's mysteries led to further research into its intricate composition. After that, Voyager 1 moved north, leaving the planet system and starting its ascent outside our solar system. On the other side, Voyager 2 set off on an extraordinary journey that brought it to the solar system's outermost planets. It made a landmark flyby of Uranus in 1986, finding 10 previously undiscovered moons, and thus expanding the number of known satellites on the planet. Voyager 2 arrived at Neptune 3 years later, exposing the amazing features of this distant ice giant. During its approach, Voyager 2 reported wind speeds of up to 1,000 mph, the fastest yet measured on any planet in the solar system. Upon approaching Neptune's methane-laden azure atmosphere at a distance of 2,180 miles, the spacecraft offered unparalleled insights into this remote planet. It was discovered that Triton, Neptune's largest moon, is among the solar system's coldest locations, with surface temperatures as low as 391 degrees Celsius. Triton also displayed unusual geological features such as ice volcanoes that erupted up to 5 kilometers into its thin atmosphere, spitting frozen particles and nitrogen gas. These findings have greatly increased our understanding of the variety and complexity of celestial bodies in the furthest reaches of our solar system. In addition to expanding our knowledge of the outer planets and their moons, Voyagers 1 and 2 have contributed priceless data during their interstellar travels. The culmination of Voyager's study of the heliosphere, a huge bubble-shaped area of space dominated by the solar wind, was the crossing of the heliopause, the point at which interstellar space begins and the Sun's influence diminishes. In 2012 and 2018, respectively, Voyagers 1 and 2 became the first human-made objects to enter interstellar space. This transition advanced our knowledge of the boundary between our solar system and the rest of the galaxy, providing scientists with invaluable information on the characteristics of magnetic fields and interstellar plasma. Astronomer Carl Sagan was instrumental in the missions going beyond their original objectives. As a member of the Voyager imaging team, Sagan strongly supported taking one last round of pictures before the cameras on board. Both spacecraft were shut down, a farewell gift to humanity. His perseverance was rewarded when Voyager 1 aimed its camera back toward the inner solar system on Valentine's Day in 1990, capturing a set of 60 images. The most famous of them, dubbed the pale blue dot, remains an enduring representation of our place in the universe. Taken from a staggering distance of 3.8 billion miles away, Earth appears as a small, pale blue speck that is hardly noticeable, a humbling reminder of our place in the vast expanse of space. The Voyager missions read like a story of space-age superheroes, enduring for over 40 years while sending useful data from the farthest regions of our cosmic neighborhood. Let's now discuss their outdated technology, specifically the 8-track cassette system. Yes, you read that correctly. The Voyager probes still utilize 8-track tapes, a popular data storage medium in the 1970s. The longevity of these reliable cassettes is a testament to the brilliance of the mission's creators. But why use 8-track tapes? Digital storage, as we know it today, was very new during the early days of space exploration, so the engineers needed a dependable and durable solution. The 8-track tapes worked well, serving as the cosmic age's unbreakable workhorses. Even more astounding is that the data stored on these tapes contains priceless scientific information about the outer planets, their moons, and interstellar space. Not just ordinary music. These tapes hold the key to unlocking some of the universe's greatest mysteries. Despite the harsh conditions of space, including extreme temperatures, the vacuum, and cosmic radiation, these elderly adventurers continue their journey. It's like sending your grandparents on an Arctic hike, where they not only survive but thrive. The deep space experiences of Voyager 2 with Uranus and Neptune were equally revolutionary. During its approach to Uranus, Voyager 2 discovered many moons, including the fascinatingly active Miranda, as well as a complex magnetic field. Then, in 1989, Voyager 2 delivered humanity's first detailed photographs of Neptune, revealing its vibrant atmosphere, deep blue color, and the Great Dark Spot. Additionally, the spacecraft confirmed that Neptune has faint rings and discovered 6 more moons. As they traveled farther into space, the Voyager spacecraft continued sending back crucial scientific data, including information about the heliosphere, the bubble-shaped area of space dominated by the sun's magnetic field and solar wind. After passing through the heliopause, which marks the edge of the heliosphere, the Voyagers explored the sparse interstellar medium between the stars. One of the most astonishing recent discoveries is the unexpected rise in cosmic rays found in interstellar space, which has led scientists to reconsider their theories about the interstellar medium and the environment beyond our solar system. NASA has implemented policies to preserve the Voyagers' remaining energy and prolong their missions as long as possible. As they near the end of their operational lives, the spacecraft are anticipated to continue until at least 2030, provided their energy supplies are carefully managed and non-essential systems are shut off. During this period, the data they return will significantly enhance our understanding of the interstellar medium and the outermost regions of the solar system. The endurance and success of the Voyager missions are a testament to the inventiveness and dedication of the scientists, engineers, and technicians who designed, built, and managed the spacecraft. The Voyagers have persevered through extreme conditions and great distances, returning data that has revolutionized our understanding of the solar system and beyond. These missions have also underscored the importance of robotic exploration in advancing our knowledge of the cosmos. The understanding of gravity assist techniques proved crucial to the Voyager mission's successful implementation of multiple key concepts, making their interstellar voyages legendary. Imagine Voyagers 1 and 2 setting out on their daring mission to explore the furthest reaches of our solar system. To reach these distant destinations and collect priceless data, they needed more power than their propulsion systems could provide. This is where gravity assist came into play, acting like a cosmic dance. The spacecraft used the powerful gravitational attraction of heavyweight planets to propel themselves forward, saving fuel and increasing speed, allowing them to visit more destinations on their grand tour. A gravitational slingshot, or gravity assist, is a technique where a portion of a planet's velocity is transferred to the spacecraft as it passes. Imagine Voyager 1 approaching Jupiter, a massive gas giant with strong gravity. At the right angle and speed, Voyager 1 received the necessary acceleration as Jupiter's gravity pulled on the spacecraft. But this maneuver is no easy feat. It requires an extraordinary level of precision. If Voyager 1 had approached Jupiter at the wrong angle or speed, it could have resulted in a cosmic disaster. However, NASA's brilliant engineers and scientists made the right decisions, allowing both Voyagers to embark on a remarkable journey through the solar system. For example, Voyager 2 reached Uranus and Neptune with the help of gravity from Jupiter and Saturn. These cosmic slingshots were essential to the success of the Grand Tour, Without them, the Voyager missions would not have been the same. Thanks to this precise use of gravity assist, Voyagers 1 and 2 were able to reach interstellar space. Although simple in concept, gravity assists are incredibly challenging to execute. In addition to gravity assists, the Deep Space Network, DSN, played a significant role in the Voyager mission's success. The DSN consists of large antennas and communication facilities spread across the globe, enabling interplanetary spacecraft missions. The DSN maintained communication with the spacecraft during the Voyager missions, allowing scientists to exchange data and send commands over billions of miles. As the Voyagers traveled further from Earth, their communication systems became even more critical. The DSN's 3 locations, in Australia, California, and Spain, ensured a constant connection, allowing scientists to gather crucial data. Without the DSN's involvement, these missions might not have achieved their groundbreaking success. What makes the DSN so crucial is its ability to receive faint signals from billions of miles away, boosting the weak signals that Voyager sends. The DSN also transmits commands, ensuring that spacecraft receive updated instructions and continue their mission successfully. This two-way communication is vital for the success of deep space missions. The DSN's global network of antennas allows for continuous communication with spacecraft, ensuring that even if one facility is out of range, another can maintain contact. This redundancy is essential, especially for missions like Voyager, where losing communication for even a brief period could mean the loss of critical data. Moreover, the DSN uses sophisticated atomic clocks to ensure precise timing for spacecraft tracking and data interpretation. These clocks enable accurate spacecraft navigation, ensuring they stay on course and reach their intended destinations. An important milestone in the Voyager probe's interstellar mission was crossing the heliopause, the boundary where the influence of the Sun's solar wind diminishes and the vastness of interstellar space begins. The precise location of the heliopause was long debated, but when Voyager 1 crossed it in 2012, it confirmed predictions made by astronomer Bill Kurth in 1993. However, the heliopause encounter raised new questions. Although the plasma density increased as expected, there was no significant change in the direction of the magnetic field, a finding that surprised scientists. Voyager 2, which crossed the heliopause 6 years later, observed the same phenomenon, challenging previous models of the heliosphere. These surprising findings have caused scientists to rethink their theories about the interaction between the heliosphere and the interstellar medium. Despite these challenges, the data from the Voyagers have provided invaluable insights into the composition of the interstellar medium. As Voyagers 1 and 2 continue their lonely journeys into interstellar space, they leave behind the planets and moons they once called home. What awaits these unstoppable travelers remains a cosmic guessing game. Voyager 1 is headed toward the constellation Ophiuchus, while Voyager 2 is moving toward the constellation Cetus. Although they are expected to cease operations by 2030, they may continue their silent journey for millions of years, perhaps even encountering other star systems. Both spacecraft carry a golden record, a time capsule of sorts, containing sounds and images representing the diversity of life and culture on Earth. This record could one day be found by an extraterrestrial race, offering a glimpse into human civilization. Even as their power fades, the Voyagers continue to send back data from interstellar space, deepening our understanding of the universe. The cosmic rays, magnetic fields, and plasma densities they encounter provide valuable information about the composition of interstellar space and the mechanisms that shape our galaxy. Reflecting on the Voyager's incredible journey is a reminder of the boundless curiosity and tenacity that drive scientific exploration.